Anybody feeling brave enough to try and summarize what we covered last week? Or contribute a little bit to the summary?
Identifying the proton NMR and what components it's made out of, so like how those protons are splitting up between the carbons, what groups they're a part of, whether they're a triplet or a doublet, or how that plays into it.
Good. So you added something that was super important at the start there, and you said we analyzed proton NMR, because NMR analyzes a lot of different nuclei. Proton NMR is by far the most common and like the most important in a class like this. There were three main things, although I think that you could maybe say there's four. One of them is looking at unique signals. And that's hydrogens that are in the same exact environment, hydrogens that are in identical environments. But that's a good spot to start if you're looking totally theoretical, because experimentally, you can't always see all the unique signals. They sometimes overlap with each other, and that makes them really hard to analyze. And then the components of those signals that we were analyzing was their chemical shift. What's another way of describing the chemical shift of a signal? Sarah, you want to give it a shot?
No.
Yeah. So the chemical shift is the x-axis. So when you're analyzing a signal, you're analyzing where it shows up, and that has something to do with the functional group that it's near or a part of. That can impact its chemical shift. Then we looked at its integration. What was the meaningfulness of integration? That's chemical shift is, do they show up to the left, do they show up to the right? The number of hydrogens producing that signal. And we say the number of identical hydrogens there, the number of hydrogens in that set. And of course, if we have an overlapping of different signals, then you're just analyzing all of the hydrogens that are there. And oftentimes, even though the aromatic region won't overlap, we'll just integrate the entire aromatic region. And if we get 5H, then we know there are 5 aromatic hydrogens. 4H, there are 4 aromatic hydrogens. And the last part was its splitting pattern. And what did we get out of the splitting pattern? Yeah, you figure out its structural environment. If you have a signal that has just one peak, then those hydrogens don't have any hydrogens nearby them. They're not split. Their signal isn't impacted. We also call this multiplicity because the signal has multiple peaks. Okay. Sorry, I have a typo. I'm trying to connect here. I told you guys that I also wanted to take a look at carbon NMR, and here's how easy carbon NMR is. And I mean by take a look, like we're gonna look at it. I still haven't decided that I'll actually put this on your unit test or the exams, because I think there's something more to assess in proton NMR. In carbon NMR, which is the C13 nucleus, we also are looking at unique signals. but you won't see carbon NMR integrated. And carbon coupling is not as strong as proton coupling, which means that you don't see splitting patterns. So the only similarity between carbon NMR and proton NMR is the fact that you can gauge the functional group by the chemical shift. And here it's actually a little bit easier to try and figure out how many unique carbons there are. They actually don't overlap quite as often as proton signals do. So you can count all of the individual peaks in a carbon NMR and find how many unique carbons are in your spectrum, in your compound. And once again, the chemical shift here, or delta, ranges from about 0 to 250 ppm. In a similar way to our proton NMR, we can show this overlap of regions along that axis. What I want you to notice is that from about 160 to 220 is all carbonyl carbons. So if you have this high frequency signal far to the left, you know you've got a carbonyl in your compound. With proton NMR, it's very challenging to prove that there's a carbonyl, because carbonyl carbons don't always have hydrogens attached to them, and proton NMR only looks at the hydrogens. If you had an aldehyde signal or a carboxylic acid signal in the proton NMR, well, there's a corresponding carbonyl. But if there's a ketone, ketones don't have hydrogens attached to that carbon. If there's an ester, there's no protons attached to that carbonyl carbon. Carbon NMR will tell you if there's a carbonyl or not. And then you've got this mid-frequency range, about 100 to 140, where you see a bunch of carbon-carbon double bonds. And here, we lose the distinction that we had with proton NMR. Proton NMR distinguished alkene region from the aromatic region. But carbon NMR, those regions overlap. And then you've got everything else. This is alkane and pretty much functional group adjacent all together. But it has the same trend. As you move to the left, you see more of this de-shielding effect. Maybe not quite as much as you'd think, and with some interesting effects that come from pi bonds. You might expect the CO and CN to de-shield more than a CC double bond, but pi electrons do some really interesting things by creating their own magnetic fields as a result of an induced magnetic field. So you basically see more de-shielding as you move to the left, similar range. That's it for carbon NMR. It's not as detail heavy as proton NMR. So take a look at this example of a carbon NMR where we have, I don't know why they couldn't just extend this spectrum by another 10 ppm, and instead they had this inset that happens right here. But that's one signal, 2, 3, 4, 4 unique types of hydrogens, no integration values given, and all of these signals are produced by the same number of carbons. They're all produced by 1 carbon each in the compound, but they have different heights. So you can't just as easily look at a carbon NMR and figure out how many carbons total there are, just how many types of carbons there are. And of course, you'll notice the carbon of the carbonyl in this compound is the one that's shifted all the way left. The carbons that are close to the carbonyl are shifted more left than the carbon that is far from the carbonyl. those experience more de-shielding. Here's another one where you actually can see that there is some change in intensity. Notice how C2, C3, C6, and C1 are only present once in this compound, but C5 and C4 have a symmetry relationship to them, and so their signals are louder. But that's not a 2-to-1 ratio, is it? Again, integration, a little bit more of a challenge with carbon NMR. And then this is an interesting necessity in carbon NMR. This is a carbon NMR. Can you see the same amount of intelligible information? Like, what there do you think is important, and what should you rule out? This that you're seeing is what we call noise. The instrument is picking up signals, but it's not meaningful signals. This might be something. This looks like something for sure, but it's hard to say what is meaningful and what is not. So because carbon NMR is so dilute, there's such a few number of carbon-13 nuclei. You need to run several scans over the course of several minutes and then average them all out so that the noise gets compressed and the actual meaningful information comes out. How many unique carbon types in this compound based on its NMR? 5. 1, 2, 3, 4, 5. Let's look at an experimental spectrum. Does anybody have their compound they'd want me to look up? It's okay. You don't actually have to do any assignment with this. So it's more just like, because you picked your compound because you liked it, I want you to look at it. The assignment that you actually have around spectroscopy, oh, it's due. Is it due tonight? No, I moved it. I think I moved it on Friday because I knew we hadn't covered it. It's due Wednesday or maybe tomorrow. So you don't need your compound spectra to do this. I just think it's interesting. I'm not sure why I'm not finding benzocaine on here. But let me try for another compound, and we'll look at its carbon NMR. Okay, I don't know. You know that it shows up? Great, thank you. All right, here's our carbon NMR for it. Oops. It's a lot cleaner than the proton NMR. How many unique types of carbons do you think lidocaine has? Anybody? 7? Oh, are you talking about like this one and this one you're not sure about? Yeah. I did count those. I think those are meaningful. 1, 2, 3, 4, 5, 6, 7, 8. This one looks like 9, but maybe 10. I'm not sure what this shoulder is.
There's also one like that.
All the others too.
Little one.
60.
Oh, here?
Yeah.
This does feel like, you can see how it's wide at the bottom and then it's narrowing in. This feels like pixelation. Like this is just getting more and more narrow as it gets towards the top. But this one is wide for a very long time. That makes me think that this is almost a superimposed signal. This actually looks like the narrowing in as it gets taller. Same thing with this. I think it's just narrowing in, and the same thing here. Because you can see that same narrowing effect, the pixelation at the bottom of these. So let's look at the structure of lidocaine. Is there any symmetry in the compound? There is some symmetry. Off of this nitrogen group, there are two ethyls. So these are the same as each other. So that's 1, 2, 3, 4. Yeah, from our carbonyl carbon. 5. This looks like symmetry. 6. This looks like symmetry. 7. And then 8. So 1, 2, 3, 4, 5, 6, 7, 8. Where's that 9 coming from? Good question. Well, it says, I'm misunderstanding the structure of lidocaine. I'm sorry. This is a methyl group that they've labeled as carbon number 8. Yeah, a CH3, a CH3. So because of that symmetry, again, these are the same as each other. They actually have gone through to map them. This is signal number 1, looking from the left. Signal number 1, signal number 2, signal number 3, signal number 4, signal number 5, 6, 7, 8. Did I run off? 9. Did I get 12?
Mm-hmm.
There we go. So this was not actually the overlap. That was the pixelation of it, narrowing as it came in. For whatever reason, it just stayed wide for a much longer time. You know, this is an issue with experimental data. It's not always going to be clean for you. It's going to look a little funky. The more time you spend with it, the easier it gets. That's all I wanted to talk about with carbon NMR. Is that okay with you guys? Compared to proton NMR, a lot easier, but you get a lot less information. Proton NMR, you remember last week we ended by building a structure based off of its proton NMR. Can you do that with this? Could you have built lidocaine based on this information? No. But you could have said there's a carbonyl carbon, there's probably some aromatic carbons, and there's probably some alkane carbons. That's all that you could really say. On the note of experimental data, I also wanted to show you guys this data. This will segue us into IR. Last week, there was a lot of Nobel Prizes announced. Last week, Wednesday, the Nobel Prize in Chemistry was awarded to 3 chemists for their work in pioneering metal organic frameworks. Has anybody heard of metal organic frameworks before? No, I'm not surprised. But in the coming decade, you might hear more and more about MOFs. When I was in undergrad, I had the pleasure of working with Dr. Mondlock doing research on MOFs. And then in graduate school, I had the pleasure of working with Dr. Park researching more MOFs. So to see MOFs come in to news for the Nobel Prize last Wednesday was really cool. And I actually wanted to show you how the Nobel Prize winning material, metal organic frameworks, actually overlaps with our learning content today. First of all, when I was an undergrad, I worked with Dr. Mondlock trying to do solvent-assisted linker exchange. We called these SAIL experiments. Solvent-assisted linker exchange. MOFs are these repeating networks of metal ions with organic nodes. Excuse me, metal ions that act as nodes with these organic linkers that create this three-dimensional porous material. In Dr. Mondlock's lab, we were looking to exchange those organic linkers for different organic linkers. So my job was to take a material called ZIF8, and I would put in a different organic molecule in an organic solvent, and I'd mix it around, and then I'd isolate the MOF again, and to see how much of the new linker I had put in, I would digest the MOF and put it into the NMR. And the NMR would give me signals. This is a signal corresponding to the original organic linker, and this is a signal corresponding to the new organic linker. And I could quantify how much of the old was still there and how much of the new was still there by looking for unique hydrogen signals. In Dr. Park's lab, we were looking at designing new materials. There was a well-established compound called copper THQ, that's tetrahydroquinone, a reduced form of an inorganic molecule. Anyways, we would take this compound that had 6 oxygens on it, and we would coordinate this organic compound with these metal ions to create this 2-dimensional sheet. We were working with copper, and copper preferred a square planar geometry. So in synthesis, we would get these sheets that stacked on top of each other like paper. And because there was a conjugation, an uninterrupted series of p orbitals, you could actually push electricity through that material. Electrons would become excited in these conjugated organics, and their electrons could be pushed through the d orbitals of the metals. And so you could push electricity across this material. We wanted to see if we could change that 2-dimensional material into a 3-dimensional material. We wanted to take advantage of these unused coordination sites on the copper. So I took a different organic compound. This is bipyridine. Bipyridine has a nitrogen inside of 2 6-membered rings, and the nitrogen was able to then bond to 1 copper below and 1 copper above, and it would take these sheets of materials and pillar them, transforming it from a 2-dimensional material into a 3-dimensional material. We wanted to know what change does that have on electrical conductivity. How much is electrical conductivity transmitted between the sheets, and how much is it transmitted through the sheets? And what new properties does our compound have? Can we utilize it for anything different than copper THQ? Well, I needed to prove that I was actually putting bipyridine into the material. So I took the starting material, copper THQ, I took the bipyridine compound, and I took the mixture of them, copper THQ bipi, and I analyzed their infrared spectra. And this is where we're segueing today into our new technique. There's a lot of information in these 3 graphs, but you can see that the place I was most interested in looking was along this orange dotted line and this green dotted line. There's a signal here on the orange graph that corresponds with this orange dotted line. And this actually tells me about the CN bond in bipyridine, this copper nitrogen bond. In bipyridine alone, the signal for the CN bond shows up at a specific wave number. In order for that bond to stretch, it absorbs a specific frequency of light. But when I bind the nitrogen to copper, I change something about the carbon-nitrogen bond. I change nitrogen's behavior, which means I change how it behaves with the other things it's bonded to. So to prove that I had actually inserted it into my material, I noticed that the signal shifted? By a lot? No. But it's not bippy sitting in my copper THQ. If I had bipyridine just sitting with my material and not actually inserted between the coppers, well, then I would expect this signal to be at exactly the same frequency. It should be absorbing the exact same energy to make its CN bond vibrate. But it's not absorbing the exact same frequency, it's absorbing a new frequency. The bond has changed. And I know that it's changed because that same absorption has shifted here. And you can see this signal in green is very sharp. There is a similar absorption in blue, that's just the moth beforehand, but that's not a sharp peak. So by looking at the change in frequency and by the change in intensity, I was able to say with certainty, yes, bipyridine is being coordinated into this material. I'm looking at how its bond has changed by looking at how it interacts with light. So here's our basis for IR. Unique bonds interact with light in unique ways. We're going to look here at our IR spectrum. On the y-axis, we're plotting percent transmittance. That is, in my instrument, I'm shining a certain amount of light towards my sample. At the top, 100% of that light is coming through. This is basically our baseline. No light absorbed. Remember that light, electromagnetic radiation, can interact with electrons. It can transfer that energy to electrons. But it can only transfer energy to electrons if the exact energy of the light matches an exact transition of that electron energy. That's quantum mechanics. Your car can go from 0 to 60, and it experiences all of the speeds in between as well. It's a continuum of acceleration. Electrons are either 0 or 60. Electrons don't gear up to speed. So electrons will either absorb light or they will not absorb light. It depends on whether they can allow that transition. When it absorbs light, we see these peaks. Sometimes these peaks are broad. Oftentimes these peaks are sharp. Sometimes these peaks are shallow. Sometimes these peaks are deep. But I want you to notice that this is an absorption peak. Some of you might feel like it should be called an absorption valley. I respect that. But we're looking at transmittance, so the peak goes down. You guys can agree to that? All right. Along the x-axis, we're looking at wave numbers, which is probably not a unit any of you have ever heard of before. It has units inverse centimeters, centimeters to the -1. And we're looking at light, right? Light has two components, wavelength and frequency. With wave numbers, are we reporting the frequency of light Or are we reporting the wavelength of light? Now that you've thought about it for a second, check with the people next to you. What do you think? Wavelength or frequency? Indigo, Natalie, you guys want to confer with each other? What do you think? Sorry, I had a long night last night. Wave numbers. Frequency or wavelength? Wavelength. Yeah. What you guys? Frequency. So what did you decide? Raise your hand for wavelength. Oh, that's one table. Wave your hand for frequency. Oh, that's the rest of the tables. What gave it away? Why is wave numbers inverse centimeters frequency? Huh? Okay, so you were like, well, because it's not wavelength and it's wave numbers, I think it's not wavelength. Why don't we just call it frequency?
Is it because it's like the inverse value?
Yes.
Yeah.
It's some number per centimeters. Anytime you have per, that's a frequency. Remember parts per million, which was the chemical shift of NMR. That is frequency, parts per million. Wave numbers, some number per centimeter. That's how many waves you see per centimeter. That's a frequency. Typically, the frequency of light is reported with units of inverse seconds, per seconds, also called hertz. But here we're looking at wave numbers. And the range for our wave numbers, on the left-hand side, we look at 4,000 wave numbers. And on the right-hand side, we look at 4,000 on the left, on the right, 400. So we go from 4,000 wave numbers to 400 wave numbers. I want you to recognize that this is similar to NMR, where the small number is on the right and frequency increases to the left. That feels counterintuitive to a lot of us. Get used to it. So here are the things that we want to analyze when it comes to IR spectroscopy. First, we'll look at the absorption frequency. You guys have already looked at the correlation tables that are on our home page. I'm actually going to pull them up again for us to take a look at. You looked at the correlation tables for the sake of the NMR, but the correlation table that takes up half of that document is the IR correlation table. You'll notice that on the left-hand side, we look at the unique bond type. And I mean unique bond type, which is why in your analysis assignment, if you're not specific enough about how unique the bond type is, then I will reject it and ask you to find the error, fix it, and send it back. Notice, I do have some things that probably could be fixed, like I say amine, but this is also true of amides anytime you have an NH. But notice that you have CH aliphatic, that's sp3ch. That's unique from sp2ch. Oh, I'm looking in the wrong spot, I'm sorry. sp2ch absorbs differently than sp3ch, absorbs differently than the ch of an aldehyde, which is technically also an sp2ch bond, but it's unique from the sp2ch bonds of the aromatic ring and the alkene. And those all absorb differently than an sp-CH. You can't just look at a molecule and say, I think there will be CH absorption. Yes, probably. Organic chemistry is the study of hydrocarbons and their derivatives. There probably will be CH absorption. What kind of CH absorption are you looking for? Because those will show up differently. And I do have to say something about this. Our textbook, Francis Carey, 13th edition or whatever, doesn't actually distinguish those two bond types, sp2ch versus sp3ch. Every other resource I have ever come across in my life distinguishes those two bond types. So if you go to our formal textbook for the class, you might not find this information, which is very odd. But it is a super helpful piece in analyzing IR spectra. You'll also notice then that I put the absorption range. And that's just like what I showed you. I was looking for a CN bond in my pyridine compound and looking at how it had shifted. There's a range where you can expect these bonds to absorb based on the surrounding bonds, the surrounding chemical structure. The exact energy of a specific bond can change. So the exact frequency that it can absorb can change. So we look at absorption frequencies. And of course, like our NMR correlation table, oh, these ranges are pretty good, but you will always find a peak that falls out of the expected range at some point or another. So give or take a few dozen wave numbers, these are pretty solid. I want to give you guys a little graph that actually helps to clarify where some of these are. Looking from 2,500 wave numbers up to 4,000, we can say that these are bonds between something and hydrogen. Notice how all of those high frequency absorption ranges, NH, OH, CH, a different kind of OH, a different kind of CH, a different kind of CH, a different kind of CH. These all absorb at different frequencies. From about 2,500 down to about 2,000 wave numbers, we see triple bonds. And there's really only two types of triple bonds that we'll come across in organic chemistry. That's the cyano or nitrile CN triple bond, or the alkyne CN triple bond. You know, I always forget to say this. Sorry. Not all bonds absorb in the IR. The only bonds that absorb in the IR are bonds that experience a change in dipole moment once they have stretched or bent. So this carbon-carbon triple bond, it absorbs in the IR often if it's bonded to a hydrogen on one side and a carbon on the other. But if that alkyne is bonded to carbon on either side, it doesn't experience much of a dipole moment when it stretches, and so it doesn't absorb IR light very well. So you can actually have a compound that has a C-C triple bond, but doesn't show this expected absorption because it doesn't experience a dipole change when it absorbs. That's another hand waviness to all of this. Starting around 1900 and coming all the way down to 1600. Actually, I'm going to bring this line down to 1500. This is the double bond region. That's where carbon is often double bonded to another carbon. Carbon is double bonded to an oxygen. Or in the case of the research I was showing you, carbon double bonded to a nitrogen. I actually don't have the carbon-nitrogen double bond on here because it's not as common of an absorption. It's not something you look for as often. Then you'll actually notice an outlier. What is that guy? NH. We said all of the bonds to H already absorb in this high frequency range. NH is showing up a second time. It's actually absorbing a different way. At the top, we were looking at the NH bond stretching. And here, we're actually looking at how that NH bond can absorb energy by bending itself instead. And that takes a different amount of energy to stretch versus to bend. And so it absorbs down here where we expect usually to see double bonds. Now this line at 1500 is an important line. This separates two regions for us. To the left is the functional group region. That's where most of our functional groups absorb. That's where we get a lot of important information. And to the right of 1500, we call the fingerprint region. I think the name kind of speaks for itself, but there's a little bit of nuance. A lot of different bonds absorb in the fingerprint region. And they absorb in very unique ways. So if you have two compounds that have the same functional groups, their functional group region will look very similar. But their fingerprint region will actually be unique. It's a fingerprint to that molecule. The thing is, there are some bonds that only absorb in the fingerprint region, and that can make it really challenging to know if they're there at all. A lot of bonds absorb there, but these bonds only absorb there. So if you see a signal in the fingerprint, it's not easy to say if it belongs to one of these. But my table would have had to be a second page if I wanted to show you all of the other bonds that also absorb there. So this is the hardest region to correlate to a bond type. Hard to correlate. It's like there's too much information down there. I want to see if I can clarify this. I know it's confusing. I had an OChem 2 lab student. I don't think they took OChem 1 here, and some schools don't really do a good job of teaching spectroscopy at all. Each week, they took an IR of their product, and they submitted it in their report. They analyzed the IR. 1 week in OChem 2, they synthesize benzocaine. Here's benzocaine's structure. You can see there's an amine, an aromatic ring, and an ester. Every single week, no matter what compound was being synthesized, this student would tell me, this compound has alkyl halide. One of the functional groups in my compound is alkyl halide, because they were seeing absorption on that far end of the spectrum in the fingerprint, and they said, well, the only thing that it could be is a C to X bond. Is there any alkyl halide in benzocaine? No halogens at all. No alkyl halide. So a better answer would have been in their report to say, confusingly, benzocaine has no halogens, no alkyl halide compound of any type has been used during this synthesis in any way, and yet there are still signals that correspond to a CX bond. And the answer is, it was something else causing that absorption. But that was the confusion about my limited correlation table. Because my correlation table doesn't say also a bunch of other bonds absorbed down here, they were left to assume those signals at the bottom of my spectrum must correlate to something on this table. So what I'm going to say to you guys is, we don't often analyze the fingerprint region. Not in my class. You can, you're welcome to, with a grain of salt, right? If you know what is plausibly in your compound, then you can try to ascertain which of these peaks it might be. And if you know something can't plausibly be in your compound, don't try to correlate it to one of these bonds. Yeah? On your analysis assignment, your job is to take your compound, and you don't need to look at its SDBS spectrum. In fact, your job is not experimental, but theoretical. Look at your compound and identify all of the bonds that are present and show where you would expect them to absorb based on this correlation table. And if you have bonds that show up down here, for instance, if your compound is benzocaine, and you're trying to show where the CO single bond absorbs, well, it only absorbs in the fingerprint. You don't have to worry about that. On your unit test this weekend, you'll be given an IR, and you will have the job of correlating all of the major peaks north of 1500. I'm not going to ask you to correlate the signals that you see below 1500. Does that make sense? We're making that distinction between the functional group region, where it's easy to ascertain bond type, and the fingerprint region. Okay? All right. There is something to be said. There's something to be said about absorption ranges. It's not always clear and perfect. Oof. Some unique bond types overlap. So you'll notice in the carbonyl range, this region right here, the CO bond of the acid halide and the CO bond of the anhydride, they pretty much absorb in the same range. So if you see absorption in that range, you might be able to speculate it's one of those two without being able to say for certain, just based on that signal, which one it is. Not to mention, this range comes down to 1770, which means it overlaps a bit with this next range, which starts at 1775. And that is a shared range between carboxylic acids and esters. And that range overlaps quite a bit with this other region that starts at 1740 that shares aldehydes and ketones. And that range overlaps a little bit, 35 wave numbers, with the region for amides. Not to mention, we said that this table is pretty good, give or take a few dozen wave numbers, depending on how those bonds are surrounded in the structure. Which means you might see a signal at about 1680 that belongs to a carboxylic acid pretty unexpectedly. But this whole region, the carbonyl region, tells you you've at least got a CO double bond. You might have to do a little bit more work to ascertain what CO double bond that is. Here's a nice one. The sp2CH and the sp3CH never overlap. That's really nice. It actually means that on the IR spectra that I give you, I can make two really nice lines. I will always provide these lines. I will draw a dotted line right at 3,000 wave numbers, and a dotted line right at 1,500 wave numbers. What is so useful about 3,000 wave numbers? That's the cutoff between sp3CH and sp2CH. So if you see that dotted line, and there is absorption just to the left of that dotted line, you know that you have sp2CH. And if there is absorption just to the right of that dotted line, you know you have sp3CH. If there is both, you know you have both. If one of them is missing, then you can ascertain which one is missing. That's really important because two of the most common bond types in organic chemistry is the sp2CH bond and the sp3CH bond. A little bit of terminology, aliphatic just means alkane-like, but not all sp3CH groups are part of an alkane carbon. If I have an alcohol connected to an sp3 carbon, then technically the hydrogens bonded there too are part of an alcohol group. So it's not necessarily alkane, it's just aliphatic. New terminology. Honestly, I want you to correlate aliphatic just with this idea of being sp3 hybridized.
Is it just sp3 for CH, or is that just sp3?
Aliphatic, sp3 for CH.
Okay.
Yeah. After looking at the absorption frequency, we look at the absorption, peak. We look at the number of peaks. On the far right side of this correlation table, you'll see that every now and then it says primary amine, that's NH2, 2 peaks. Secondary amine, that's just NH, 1 peak. There's a signal, a peak, for each NH bond. And then you come down to this, sp3CH, 2 or 3 peaks. CH of the aldehyde, not vague, specific, 2 peaks. And then the rest of them, they just kind of say, for the most part, several peaks. Here we go, aromatic overtones, several peaks. The nitro group, 2 peaks. And then others just describe the shape. So number of peaks and shape. Let's look at this lidocaine example again, because lidocaine has some CH peaks, which will help me explain some of this. Here we're looking at 3000. These signals just to the right of 3000, those represent sp3ch absorption. And you can see I've got several peaks here. Really don't worry about counting them. This is another one of those hand wavy things where you have to just kind of say, are there peaks there? Yeah, good. And the question can become, if a CH bond absorbs a specific energy, then why are multiple energies being absorbed? And this has something to do with there are different CH bonds. There's the CH3 CH bond and the CH2 CH bond. So different nature of different bonds can absorb in different ways. And there's multiple bonds. So if one CH bond absorbs an energy and is now stretching, it's changed the nature of its bond, which can impact the nature of a neighboring bond to absorb a slightly different energy now as well. So we often get these packets or these sets of peaks. And you don't count them all individually. Instead, you can just say, oh, look, they're all in the expected range. From 3000 to 2800, great. All of my peaks were found in that region, so they likely all belong to the sp3ch. If I had a physical printout of this, or if my screen was up, I could just circle all of these peaks. This set right here, this packet of peaks, those all represent my sp3ch. There's some unique ones. I want to point out the CH of the aldehyde. The CH of the aldehyde is always this set of twin peaks. So here we go again, where I'm looking at 3000, and I have a lot of peaks to the right. Okay, well, I'm going to cap my search at 2800. And that seems to be right here. These two really fit into the sp3ch the most. These two really don't. Looking at my correlation table, the CH of the aldehyde absorbs twice, 2 peaks, sharp, one at 2800. That is the bottom of the aliphatic range. So if it's at 2800, it might not actually be the sp3ch. And it's twin at 2700. So if both are there, the signal at 28 is definitely not part of the aliphatic. It's a part of this set. I do want you to notice that saying 3000 to 2800 is different than saying 2800 and 2700. That's not here through here. That's this and this. 2800 right here. 2700, right here. Twin peaks, indicating that I have the CH of an aldehyde. Now let's talk about some shapes. Truly, the only two bond types that are not generally sharp are OH bonds. Sharp comes down at an absorption, goes back up, absorbs, goes back up. Sharp, sharp, sharp. All of these are sharp. Not this guy. Very broad. Has a broad absorption. And I want to tell you what that means. That means that a bond like this is absorbing pretty much an exact frequency. It's just that energy of light that allows its bond to change, stretching or bending. But what about this guy? It's actually a lot of different frequencies that allow its bond to stretch. Why? Why is it that the OH bonds can absorb a much broader range of frequencies in order to get their bond to vibrate? Any ideas?
Is it because of how uneven the split between the oxygen and the hydrogen is compared to everything else on there?
Talking about electronegativity?
Yeah, I'm just thinking
Kind of.
what we've talked about in the past.
I think I saw this the other day. Because of the forces, it's a hydrogen bond.
Yeah. Hydrogen bonding with other molecules in the sample being analyzed. So I'm looking at an OH bond, true, but I'm also looking at an OH bond that is interacting with a neighboring OH bond. So the nature of my bond depends on how concentrated the sample is, how close that one molecule is to another molecule, and how it being hydrogen bonded is impacting the other bond types. Yeah? Because of hydrogen bonding, we get these broad OHs. The OH of an alcohol shows up broad, typically like this. But the OH of a carboxylic acid, we say it's very broad. This is a broad absorption. It stretches pretty wide, but it's nothing compared to the carboxylic acid absorption. In fact, the carboxylic acid absorption is so broad, sometimes it's hard to even say that it's a signal in and of itself. There are some compounds that you'll see the IR says like free. If a sample doesn't have any hydrogen bonding, then that absorption goes from being broad to being very narrow, because now the bond has a specific energy type. Let's look at a carboxylic acid for reference. Yeah, that's not a great one. I'm going to see if I can find another one. but this is actually the OH of the carboxylic acid up here. It's incredibly broad. It's like it's hiding. And it's overlapping a lot of other signals as well. Here we go. That's not just broad like the last one was. This is incredibly broad. And a little bit more shallow. It's not as deep as the last one was. Okay, and this is the last point that I want to make here under the number of peaks and the shapes. The intensity of a signal is relative. I really hate that. You'll notice on the correlation table that some of these signals are listed as weak to medium, medium to strong, weak to medium. That is to say, does this signal absorb very well and it goes strongly all the way to the bottom, or does it not absorb light very well? And so its signal is rather weak and it's short. Some of the compounds that absorb, some of the bonds that absorb the strongest are the CO bonds. CO bonds are almost always the strongest bond type. They can make other strong absorbers look like medium absorbers relative to them. So if they're not present, medium absorbers look like strong absorbers. And weak absorbers look medium. But when they are present, then the medium absorbers look weak. So there's this range between how well a bond absorbs light compared to how well the other bonds in the compound absorb light, and what that looks like relative to each other. So to give you a comparison, first we're going to look here at an alkane carbon, an alkane compound. Look at the sp3CH absorption here. Strong, goes nearly to the bottom. Other things relative to it look more medium and weak. Okay, that's the sp3CH. That's not going to change when we look at butanone. Butanone has a ketone. Relative to the CO bond, butanone looks like the sp3 is more medium. This is one of the worst characteristics of IR, is that depending on the types of bonds present, other bonds change their intensity relative to it. All right, I realize I haven't given you guys a break yet, so why don't we take 5? Get up and move around, get your blood flowing. And we're gonna look at one last characteristic of IR before we start analyzing some compounds. as I get really worked up. I'm trying to make sure I have a good handout exercise. And I forget that I should have just brought this. Instead of flipping between the two pages, two websites. By the way, I know a lot of you were just dying for this, but I just uploaded this today to the top of our Unit 3 module. This should help you prepare for the unit test. These are our learning objectives for the two sections. So, unique signals in NMR, functional groups based on chemical shifts, integrations. By the way, I did put carbon NMR in the learning objectives. But you guys saw how easy that was to just count how many unique carbons there are. I don't think you'll see problems like that. But I'm also planning on making changes as I go forward. And I think counting the number of unique carbons is not hard. So I think that was easy enough to keep in there. Splitting pattern and construct a molecular structure. Then up here, it's like almost the same number of learning objectives. And we're already almost done with IR. We've got mass spec to talk about next time. And then we're going to tie all of them together. We're going to see if we can predict a molecule based on all of its spectral information. But this is what we're looking at. Correlate the absorption signals with unique bond types based on their wave number, shape, and intensity. That's their absorption frequency, their wave number, their shape, their intensity. I think you could consider the number of peaks to kind of be shape. And intensity is kind of shape. So differentiating those was a little bit challenging for me. And this is actually what I want to talk about next. Corresponding bond types. You guys remember what this is called? It's at the top. Correlation. You guys get the name, right? Like you're correlating the bond that you see with the signal that you, or the bond that you have with the signal that you see. And the correlation table's on the back. We looked at the proton NMR. You're correlating where the signal is with the nature of the group. But correlating and corresponding are different, and that's why I don't think that I've heard anybody else describe this section quite like this, corresponding peaks. But for me, it's like an obvious part of IR that doesn't feel obvious until you lay it out. And I hope that you guys will see that this feels obvious as well. Corresponding bonds, corresponding peaks, is not the same as correlating a signal with the bond. Instead, it's saying that functional groups often have more than one bond type. I should have started that by saying often, not even often, sometimes, occasionally. So here's something I struggle with. I think it's a personal problem. Students will fill out their analysis of the organic compounds. They'll look for the IR spectrum. They won't give me a bond type. They just give me a functional group. They say, my compound has an ester. Ester absorbs between 1775 and 1750. 1715. No. the ester does not absorb between 1775 and 1715. The CO double bond of the ester absorbs between 1775 and 1715. The CO single bond of the ester absorbs between 1300 and 1000. You can't tell me the functional group absorbs there. The functional group is made up of multiple bonds, and those bonds can correlate. For instance, if I see the CO double bond absorption and I see the CO single bond absorption, oh, well, those correspond to an ester. Or they might correspond to a ketone and an alcohol because I've got the CO bond. Yeah? So there are a few functional groups here that can be really challenging to differentiate from other things, except that they should always have more than one bond type that shows up. I'm going to start at the top, and we're going to look at the amine. The amine has the NH stretch in that high frequency range. And it has the NH bend in a lower frequency range. If I see a signal and I want to correlate it to the NH stretch, then I must also correlate it to the NH bend. Those are corresponding, you know what, I didn't mean to say corresponding bonds. I think it's better here that I say corresponding peaks. These two peaks correspond to the amine. If I see one of them and I want to correlate it to that bond type, I must also correlate the other. Yeah? Let's look at another one. And again, we'll kind of start at the high end range here. You know, alcohol is actually not that important, in my opinion, because the alcohol is pretty unique in that the OH is broad. It kind of stands alone. But if you were going to look for the OH of an alcohol, can you look at your correlation table and tell me where else would you expect to see a signal in the spectrum? If you're going to look at the IR and say, that's the OH of an alcohol, then you must be able to look somewhere in the spectrum and say, that could be what? Carboxylic acid is not an alcohol. Thank you for saying that. Which is why they show up differently, yeah? Remember actually when we introduced functional groups, and I said a lot of people confuse benzene ring for having alkenes, carboxylic acids for having alcohols, amides for having amines, but that's kind of like doubling up on the functional group. So there is no alcohol in the carboxylic acid. Good try though. If I have the OH absorption of an alcohol, then I must also have the what absorption of the alcohol? The CO absorption. Where is the CO absorption? It's in that fingerprint region, 1300 to 1000. So the fingerprint region, it's going to be hard for me to say with certainty which absorption down there is the CO absorption, but it must exist. Here's what I would like you guys to do. Using your correlation tables, I would like you to find the corresponding peaks between these next few groups. I want you guys to find the alkyne, the carboxylic acid. Would it be better if I broke these up and had you just do one of them? Yeah? Then maybe by table, you guys can tell me which ones you want to pick. Starting in the back, you guys will have first pick, but I'll get them all written up on the board first, okay? The alkene, the aromatic ring, the aldehyde, might be all that I can do. I'm also going to, yeah, I think that's it. I think I'm going to put alkane here, but I'm not going to assign it to you guys. I'm going to go through that one at the end. Maisie and Dee, which one do you guys want to do? Alkyne. Yvonne and Sarah, which one do you guys want to do? Carboxylic acid. Nicole and Yoon, which one do you guys want to do? Alkene. Indigo and Natalie, which ones do you guys want? The aromatic ring? You three? You guys want to pick one? Aldehydes? As a group 4? Or do you want to do 2 versus 2? You can choose double up. Yeah, anything you want. Let's do 2 groups of 2 then. Yeah, we're gonna have to double. Okay. All right. Spend about 6 minutes on this. Use the correlation table and find how many corresponding peaks you would expect from your functional group. What do you guys think of yours? Great. There you go. Any others that stand out?
I literally missed. I was like, he won. I was like, are we talking about there was a second? Oh, I get it now. The bond is talking about that molded.
No, actually, if there was no H, it was just bonded to another carbon. Yeah, the CH bond, if it's gone, then I wouldn't expect you to. Yeah. Good. All right, good job. Feel free to fill in some of the others. If you guys are done with yours already, fill in the ones that you didn't choose. See if you can beat your classmates. Would you guys get through the past one? Great. Good work. And the only clarity I think I had there is identify what
Live right next to Dear God. No. They look like roses.
that clarifies further, right? If I have the aldehyde, I expect the CH here and CO double bond here. And now I know the functional group has more than one bond site that I can find here. And I know where those specific bond sites are. If I see one, I'll see the other.
No, there's like a sweet spot. Like I'm getting like my exercise for the day. I'll do it.
Good. And what about
I
this?
just want to like back up and get some serotonin.
We'll talk about it. Because it's not actually a bond type that's listed, but it is still labeled as the functional group, so it's something to kind of look for. Yeah. So I'll show you guys some visuals. It is a result of the ring.
Yeah.
So you could say it's the carbon-carbon double bonding, but it's actually more than that. Because carbon-carbon double bonding is
Actually, I feel a lot better after the first. I need to get a good night's
But in different, very different regions. Yeah, 1900 to 1700. And really, I try to organize this by sources. The aromatic overtones should like.
No, I do not drink coffee.
And I like to put it next to it.
I usually just
You're looking for the carbon-carbon double bond. You can also look for these overtones. Resonance.
I've been like kind of geeky from
So you guys do. Good. Yep. We'll talk about that. It's a fun property of the ring. Because you'll notice the alkene doesn't have them. Despite the alkene also having carbon-carbon double bonds. Yeah, isn't it? So what did you find out? Fermi resonance. Fermi's a famous guy. All right, are you ready? I think I had one group that worked on alkynes. How do we define an alkyne functional group? An alkyne functional group is when you have not just any triple bond, because carbon monoxide has a triple bond, cyanide has a triple bond, but alkyne is specifically a carbon-carbon triple bond. Yeah? Alkane, carbon-carbon single bond. Alkene, carbon-carbon double bond. Alkyne, carbon-carbon triple bond. Now, if that alkyne is what we call terminal, then you can expect to find an sp hybridized CH absorption. And we saw that being the highest CH absorption, 3,300 to 3,200. And if you see the sp-CH bond, you also expect to find what? The CC triple bond, the defining feature of the alkyne. And we see that absorbs here 2250 to 2150. Now, to be fair, we didn't say that the alkyne must have a CH bond. Sometimes alkynes have carbon bonded on either side. And I mentioned earlier that only bonds that experience a change in dipole when they stretch will actually absorb light to stretch. So if there is no CH on the alkyne, then you probably won't see the CC triple bond either. So it's both of these or neither. Now, to be fair, is neither evidence of an alkyne? No, the absence of the signal doesn't indicate an alkyne. It's invisible to the IR. The IR won't tell you that it's present. What could help you? Carbon NMR. Carbon NMR would give you two signals in the triple bond region to help you distinguish that you do have an alkyne, excuse me. Now I had two groups that gave me the carboxylic acid. So let's see if you guys agree. Actually, maybe I didn't. Yeah, you guys did? You did, right? Carboxylic acid. Which one do you, what did you find? What bond types would you expect?
OH single bond and CO double bond.
And the OH single bond is different than the OH we expect from the alcohol. This isn't 3400 to 3200 broad, right? This is what? 3300 to 2500, very broad. That's a different OH absorption. I just want to point that out. OH alcohol absorbs differently than the OH of the carboxylic acid.
It's 28, not 25.
Thank you. Give or take a couple hundred wave numbers. And I think I showed you guys more than one carboxylic acid absorption, and they do look different. Unfortunately, they're the least consistent.
Can you remind me, why did you write or neither?
If the alkyne is not bonded to a hydrogen, then it likely will not experience a change in dipole in the CC triple bond.
Oh, is it because, yeah, okay.
So if this is not present, this likely won't absorb.
Because it's only, yeah.
Because you don't need this to have an alkyne. All you need is this. So there are alkynes that have CH bonds. There are alkynes that don't. And if the alkyne does not, then it likely won't absorb here either. And so you'll either see both or you won't see either.
Sorry, thanks for, I didn't mean to interrupt.
That's okay.
I realized I missed the explanation.
Now we see a lot of CO double bonds. So the CO double bond of the carboxylic acid, 1775 to 1715 for the most part. Again, you'll see examples. You can find compounds where they don't show up there. But here's a nice thing. If I have a signal between 1775 and 1715, and I also have a signal that is very broad, 33 to 2800, then I can say with certainty the CO double bond in this range is not an ester, it's a carboxylic acid. If all I knew was that there's a CO double bond in this range and I couldn't look at the rest of the spectrum, I wouldn't be able to tell you what functional group the CO double bond corresponded to. But because I have a corresponding peak at the OH, now I know confirmation about the CO double bond. It's kind of like how in NMR, the CH3 triplet corresponded to a CH2 quartet. The three hydrogens are splitting the two hydrogens into a quartet, and the two hydrogens are splitting the three hydrogens in a triplet. They correspond with each other. These correspond with each other. Different peaks can actually help you confirm your functional groups. Alkene. Here I had two groups that did alkene. Yeah? First in the back. What did you guys find? Not CH. Gotta be as unique as possible. sp2CH and the CC double bond. I'm just gonna rewrite these because personally I like mine to go from high frequency to low frequency. And the sp2ch absorbs at a higher frequency than the CC double bond. sp2ch is somewhere from 3150 to 3000 wave numbers, whereas the CC double bond is somewhere around 1680 to 1600 wave numbers. So here's the deal. If you tell me that you see in a spectrum sp2ch belonging to an alkene, you'd better be looking for the CC double bond of an alkene as well. If there is an sp2ch of an alkene, there is also the CC double bond. This is actually an and or situation, not an either or. You don't have to have an sp2ch to have an alkene, do you? You could have halogens coming off of the alkene at every position, but you still have the CC double bond. So you can actually sometimes see the double bond absorbing when there is no sp2ch. But if you see the sp2ch, you should look for the CC double bond. And these are weak to medium absorbers. And so there is experimental data that I get from students, and they say, I'm looking for the corresponding peak, I'm looking for the CC double bond, and I don't see it. Okay, that's okay. That gives you a good write-up if you're in a lab setting to say, I'd expect to see a signal in this region corresponding to the alkene, but I don't see it. Question mark, interesting, move on. It shows that you understand how to interpret it. Anybody else did the alkene? No, that was just that. All right, aromatic ring. This I had two groups for. Who was the first group? You guys want to give me one of the signals that you identified? Okay, and that absorbs? Good. I do want to point out there's a lot of resources that will give you more numbers. Like some resources will say 1600 down to 1450, but it's like 9 times out of 10. If you have an aromatic ring, the CC double bonds absorb at 1600, give or take a few wave numbers, which is different than the CC double bond of the alkene, which has a bit of a larger range. The aromatic ring is 9 times out of 10, right at 1600. Pretty convenient. And then you guys want to give me a signal that you found?
Yeah, the CC double bond with overtones.
And I'm actually going to put that right above this one.
That's 1900 to 1700.
The overtones that are listed on here are very small. I'm going to see that if I can find one. In fact, we should be able to see some in our lidocaine example. Overtones are kind of like a resonating frequency of the aromatic ring. I think that you might be able to say that these are aromatic overtones. They're in the right range for it. They're fairly weak, but they're actually not as many as I would expect. Let's look at this compound, bromobenzene. Here we see the overtones. So 1600, oh, what a shame. I don't know what happened to this experimental data, but it seems to be missing its CC double bond absorption. But then we see these several regularly repeating small signals. I'm not going to lie to you. Most of the time, I want you to ignore small signals because there's a lot of things that just make some noise in your sample, and they're not meaningful to your analysis. But these actually are useful. So it can be easy to miss overtone signals. All right, give me the last corresponding signal that you would expect to see. Good. the sp2ch, and sadly, that's the exact same range as the sp2ch of the alkene. So they share a range. So if you see a signal that corresponds to an sp2ch, like say here, here's my range for sp2ch. How do I know whether that sp2ch belongs to an alkene or to an aromatic ring? Well, I can look for some differences in their other corresponding peaks. If it's an alkene, the CC double bond might be at 1600, but if it's well above 1600, it's probably an alkene. If it's right at 1600, and especially if I see some aromatic overtones, then I know the sp2ch belongs to an aromatic ring and not to an alkene. Here's those overtones again. Aren't they pretty? They're kind of cute. And right here at 1600, CC double bond. By the way, we're just getting bond types from IR, right? We didn't get bond types from NMR. We got kind of like a vague, blurry picture of functional groups, but we didn't know any specific bond types inherently. But NMR gave us an exact structure. Can IR give you an exact structure? No. It can just tell you bond types. All right, we're in our last couple, the aldehyde. What do we have here? Good, the CH. Now technically that is the CH, it's sp2, but we're going to call it CH aldehyde because it's distinct from the sp2ch's of the alkene and the aromatic ring. And this absorbs twice 2800 and 2700, right? And then what else did you find? Here our range is 1760, 40, 1660. What other CO double bond shares that range? According to your correlation table, what other CO double bond shares that range? The ketone. So if I see a signal in this range, I wouldn't know if it's the CO double bond of an aldehyde or the CO double bond of a ketone. But if I see a signal in this range and I see the twin peaks of the CH, I've confirmed that this belongs to the CO of an aldehyde. If I see a signal in this range and I do not see the twin peaks of the aldehyde, I've confirmed that this belongs to a ketone. That's the beauty of corresponding peaks. All right, our last one was the alkane. But yeah, of course.
So are you specifying that it's an aldehyde and not sp2 because it has those twin peaks and that's very distinct? Or...
And the range is distinct.
Okay.
I don't want you to
confuse it with the aromatic ring.
Yeah.
It's just too many.
It's, I don't know, and maybe it's just like the exposure I've had to this. Anytime somebody says sp2ch, they're referring to a hydrocarbon functional group, alkene or aromatic ring. And to describe the CH of the aldehyde, despite also being an sp2 hybridized carbon, they normally don't refer to it as its hybridization, but more to the fact that it's part of a non-hydrocarbon-based group. It's part of the carbonyl group. Yeah. Ultimately, on the document that you guys submit, I'd like to see hybridization and or bond type, but with these, hybridization is something I really want to lean into. sp3ch, sp2ch. The aldehyde, CH aldehyde is great. And remember, there's wrong answers in your analysis assignments, but that's why I give you guys feedback to try and go back and try to understand it better. If we were looking for an alkane functional group, we would be looking for sp3ch, which absorbs from 3000 to 2800 wave numbers. What's the other main bond type in an alkane group? Kind of the defining feature of the alkane functional group. Carbon-carbon, single bond. Have you noticed that this table doesn't have carbon-carbon single bonds? Have you noticed that in the compounds we've looked up, carbon-carbon single bonds haven't been looked at? These have no significant absorption. So you will look at your compound and undoubtedly find CC single bonds, but there is no absorption peak to correlate to a CC single bond. So when you submit your assignment and you say, these are the signals I'm expecting to find, these are the bonds in my molecule, these are the signals I expect to see, you never have to list carbon-carbon single bonds. They don't have significant absorption. So that assignment would be a great way to apply IR that we've learned before we come back on Wednesday. On Wednesday, we'll talk about mass spec, and we'll tie all of this spectroscopy together to analyze compounds. All right? Have a good night, guys.